Alright, in this video I'm going to be discussing and demonstrating a numerical calculation I've done. It's a projectile motion and it involves air resistance, both quadratic force and linear force. Just to start, just with the basics of a numerical calculation itself, it's a model. It's not physics. And that's obvious, but you'll see what I'm talking about as we go through this. So like I said, it's a tool and it has to be used correctly, and it has to be modeled so that it would fit a real life situation. Now if you go in and just put anything's going to run according to the program. Even if it does not match the physics, it's still going to run, and you may not know about that. Now it seems like that's stupid to say, or why am I saying this, but believe it or not, when you go and do these things, lots of times small little things or maybe errors you've done will allow the program to still run. You're still going to get a graph, you're still going to get a visual, but it does not model correctly real physics. And to prevent these things, you have to know your model. Okay, so when does your model start to fall apart? You know, when can you not use this model? When should you use this model? What conditions, what situations? Okay. For example, before I did this, I only used the linear force for the air drag, and then as I was going about things, everything looked fine. It started off as a path. You could see it started to lose velocity in the x direction. It looked like what you'd expect from all the graphs you'd see in a textbook. It looked fine. I thought it was fine. But it did not resemble reality, because I started to think about it, and I only used a linear term. Okay, so it's still going to give you some drag, but if you look at the equations, there's a little trick you do. You do the quadratic term divided by the linear term to get a ratio. Turns out if that's really big, like 1,000, then you could just go ahead and use the math or even model a numerical calculation only with the quadratic force, get a good answer. If your ratio is very small, that means in the denominator, which is the linear force, that's really big, a linear force, and it dominates the equation, and you'll be just fine using this numerical calculation. Turns out though, in almost all the situations I used, I actually printed the ratio to the screen, and it turns out that almost all the cases were 200-300. So that means the quadratic force was 400 times greater than the linear force. That model is incorrect because I only used a linear force. Now it looks correct, you know, you'll see it start to taper down, but going back to know your model, that in those parameters and most of the masses and B values, that model fell apart and it didn't work, but it looked like it did. So you really have to be careful. Okay, let's see. Okay, another thing to do is test extreme conditions. If you're doing projectile motion, make velocity 0. You should expect the ball to fall. If it just starts going with some movement, you know something was wrong. You know, test the gravitational force is 0. You should see a linear path if you give it velocity. If not, it should just stay absolutely still. You know, if you're using drag force, it really increase that air force and see what happens, or really decrease it, and you should expect more of a quadratic or a parabola. So these just are things to keep in mind to make sure your model works. And hopefully now you understand what I mean when I said this is a model, not physics. And of course, that's the case, but it's easier than you would think to have a model work, quote unquote work, and run on the screen, but it really not resemble physics at all. Okay. So let me just quickly run through the details, and then hopefully I could show y'all it run. Okay. So this is just a floor I've made and a roof. Just the balls on the roof, and it launches at some angle and it stops when it hits the ground. These are just the vectors I put in as a gravitational vector. Again, these are real life materials. Instead of typing a mass to keep it more realistic, I've actually looked up the densities, and I will actually get the density by applying I'll find the mass by applying the density times the volume. And I took diameters of common things you would find: rain, hail, and this is the oil drop experiment with the electric force. This is the diameter, about the diameter of the oil drop. Now this actually didn't work in this model just because the diameter was so small and the time step was too big. And again, that's just more things you'll have to work on when you do these things. And then here I just, for convenience, row underscore, all those were row underscore. I could just replace this and simply just change the density. And I can actually type in a manual. I can manually type in one, or I could type in a diameter of something known like rain or hail. This is just going. This is all the values: the B value, C value, the formula, initial velocity, the angle turns it to a vector. The vector times the initial velocity. Ball.m is a scalar multiplied by the already velocity vector, so the momentum is a vector. These are just little things. I did v hat and g hat, the unit vector in the direction of velocity, unit vector in the direction of gravity, so I could just to have some more insight. I was talking about the formula for the ratio. Where's my mouse at? I've condensed it down right here, and print to the screen, so you could just have some knowledge of what's the driving force, or what's the most dominant force, quadratic or linear. And this was installed because before I did the quadratic force, I only had linear. Talking about parameters earlier, when I ran this model, if this number was too big, I knew what was going on the screen was incorrect. And it did not resemble what would really happen, only until that number was fairly small. But I just put it in anyway so I could model, a larger range of situations. Okay, this is a while statement. Real quick, it's just if this statement is true mathematically, it'll run anything that's indented. After that's done, it will repeat itself. It'll ask the question again, is this true? If so, I'll run it. Turns out this right here is the ball's position is greater than the Y position is greater than the Y position of the floor. In other words, if it has not hit the floor yet, it's going to run. So it's going to run until it hits the floor. Okay, so this is the force. I have the force of gravity in the down direction. I have the linear term, which is against the velocity of the object. That's negative b vector v. And this is the quadratic term, negative c magnitude v times vector v. And I've went out and did those. Now this calculates it and gets a vector. These are all vectors. So this is the resulting vector, and I multiply by time step dt. Force times time is change in momentum, or force times change in time is change in momentum, plus the original momentum. This is not algebra. This simply takes everything to the right, calculates it, and then assigns it to this ball.p, which is, where's my mouse at? Which is the momentum. So force times a change of time gets momentum plus the already existing momentum, and then I take the momentum divided by mass, which would give a velocity, and then velocity times change in time is position plus the original position. So you can see this just updates, and it calculates a small time step and then recalculates again and again and again. This is why numerical calculations are so helpful. This right here is just the V hat and the force of gravity hat, just arrows I've put in to show the directions. Okay, and at the very end I just put a program it to print out the position. The ball.position.x is the x position of the ball. So let me go up to give a little more insight before I run it. We are doing styrofoam. I've looked up the density of styrofoam, and this is 10 centimeters. Okay. Now you're going to see it's on a roof at some angle I've assigned it. Okay, and there it goes. If you look close, you can see quickly that it will lose its expected parabolic path had there been no air resistance. So you quickly see it approaches an asymptote right here and falls down. Now this, like I said, is styrofoam, and it just calculates the mass of the styrofoam based off of the density times volume. Now let me this is water. Okay, so you can imagine maybe a water balloon of some sort, assuming it keeps its shape, but for simplicity it's just water right now. I don't think I did ice. Oh, I did. It doesn't matter. Okay, and as you expect, because this has more kinetic energy, it would keep a path. It would keep more of a parabolic path because it has more kinetic energy. The resisting air force is completely dependent on velocity. So the same force that is applied on this is the same that was to the styrofoam. Not entirely, because the velocity was different points, but it's only velocity dependent. So it's going to take a lot more time for this to deplete. Okay, that was water. Now one more, and in my experience, just because the time steps are not exactly approaching zero, if I make the diameter too small, it tends to mess up. So it might happen, but this will be our last run, and we're making this smaller. So this is going to a centimeter right now, closer to a raindrop. So we'd expect more of a dampening effect. And as you can see, there's a lot more dampening effect here because the raindrop itself now weighs less. So anyway, that's my video, and I'm going to in the future put up more videos with stuff just like that. All right.